Last week, we discussed the Dennevit-Hartenberg transformations. It's a convention by which we can represent the forward kinematic map of a robot. Now, this is a convention that's widely used, and at first, it may be a little bit difficult to understand, but through practice, reading the textbook, doing the assignments, you'll be able to pick this up. It's not a hard thing, it's just something that's new. So what we'll do today is let's review the Dennevit-Hartenberg notation and then go through some examples. When we go through these examples, I want to remind everyone this is an active sport. You're going to have to work out the examples, do the practice problems from class and the textbook, and then try your best to do the homework assignments by yourself. So this picture here sort of summarizes what's going on with the Dennevit-Hartenberg parameters. We're going to talk about the transformation that we need to go from the end of link I minus 1 to the end of link I. Recall that the z-axes are the axes around which the degree of freedom occurs. So here, link I, zi minus 1 is associated with joint I. So joint I with zi minus 1 rotates link I. Here is a zi minus 1. Here is zi. The common perpendicular between zi minus 1 and zi, in other words, the shortest path between those two lines, is denoted by this red line here, a sub I. The length of a sub I is called the link length. When we describe the xi axis, that axis will be collinear with a sub I. The amount of rotation that we need to get the axis when it's oriented with zi minus 1 to zi is going to be called the twist, alpha I. So we rotate around this xi axis by amount alpha I to get our z-axes to line up. So now let's look at the final two parameters. Here we have the previous link length, and its x-axis is collinear with that link length like so. Here is the zi minus 1 axis. What we want to do is rotate this x-axis around the zi minus 1 axis by amount theta I, so this x-axis becomes parallel with the new x-axis. This is called the joint angle. Note that the points at which the common perpendiculars meet the zi minus 1 axis are different, and the distance between those 2 points is called the offset, d sub I. So the Dennevit-Hartenberg transformation is a series of 4 transformations. It's a rotation about the zi minus 1 axis by amount theta I, then it's a translation along the zi minus 1 axis by amount di. Then we can translate along the new xi axis by an amount ai, and then finally we rotate the twist around the xi axis to get the zi axis to line up. Now let's go through the steps by which we assign the parameters and ultimately derive the forward kinematic map. In the first step, what we're going to do is assign the z-axes to each of the degrees of freedom. In this figure here, a circle with a dot means the z-axis is coming out. If you want, we can use a circle with a cross to connote the z-axis going into the whiteboard. This robot has a degree of freedom here, a rotational degree of freedom here, a prismatic degree of freedom, and then finally one more rotational degree of freedom about an axis that's in plane with the projector. So we'll have z0 come out, z1 come out, z2 is lined up with the prismatic joint, and then z3 points along the z-axis. We also want to remind ourselves that we're going to follow the right-hand rule. Since the z-axis is coming out of the projector, my thumb going out, this is positive rotation, and then positive displacement is this from 0 to infinity. The next thing that we need to do is assign the base frame. And the origin of the base frame is chosen at our convenience. Here, we'll just put it right at the degree of freedom with x0 pointing forward. So now that we assigned the first frame, the origin of this frame, and then its x-axis, we're ready to assign the rest of the other frames. So here, we should acknowledge that there are three cases by which the other frames will get assigned. One is that the zi axes are not coplanar, meaning that they're skew. The other is that they're parallel, and then finally they intersect. When these lines are not planar, it's a pretty straightforward process. We look for the common perpendicular between the z-axes. The x-axis is parallel to that common perpendicular. When they're parallel, we actually have an infinity of choices, so it makes sense to choose an x-axis that would give us a 0 offset. You don't have to do that, but it's a nice convention. Finally, if the z-axes intersect, we choose the origin first, and then we have a wide latitude as to how we choose the x-axis. We just have to make sure we satisfy these perpendicularity requirements. For the last step, the end effector, the convention is that the z-axis points in the direction in which the end effector is reaching. The y-axis is the direction in which the end effector is squeezing, and then of course we get the x-axis from the right-hand rule. At this point, what we're able to do now is create a table where each row of the table corresponds to a transformation from the 0 frame to the 1 frame, the 1 frame to the 2 frame, and then from the 2 frame to the 3 frame.